Okay, guys, the box for the homework is coming around. Make sure you drop your homework in there, and if you miss it, just drop it off on the way out the door. Welcome to the third week, Monday, September 10th. So you can see I've populated the syllabus for the week. I've got the web work stuff up there, and some star problems at the moment, only 2 star problems. I may try to add another one for Friday just to make it one a day, because it's good for you. Also, in the supplementary section of today's work, you'll notice that I refer to a section of the book that we actually haven't talked about. That is a review or a discussion of what are called parametric equations, which some of you may have seen in other math classes. And either you remember them and you don't need it, or you don't remember them or you haven't seen them, and this is maybe a good place to review that idea, because the stuff that we're going to talk about today, and really this whole chapter, space curves, really space curves are defined parametrically, and if you don't know what parametrically means, don't worry, that's one of the things I'll explain today. Okay, so we've got these star problems, and again, as is our routine, those will be due Monday, September 17th. But don't forget that the web works are actually due as we go along. So today's web work will be due on Wednesday. There will be a little bit of modification in the homework schedule here for the exam week. You'll notice that I moved the exam from Monday, September 24th to Friday, September 21st. So athletes in the room, take note. If you've got events or whatever, make sure that you get with me as quickly as you can about rescheduling or whatever. There's going to be a review day here, a review of Chapter 13 here. So there'll be some new material here and some problems. I haven't decided when you're going to turn those problems in yet, so we'll talk about that as we get closer to the date. Okay, so the box is going around. You're turning in your homework. Are there any questions about homework or whatever problems that have been puzzling you before I get on with today's work? Okay. So today we start the topic of space curves. We've got vectors and points under our belts. We've got dot product, cross product under our belts. We've got different coordinate systems squared away, presumably. Now what we're about to embark on is, I think, one of the fundamental building blocks for vector calculus, and that is the space curve. Everything that we do for the remainder of the semester really depends on a good understanding of what a space curve is. So what I'm going to do today is show you a couple of computer demonstrations of space curves, and we're going to talk about the geometry of space curves. We're going to talk about how space curves represent motion, and then if we get a chance at the end, we'll actually start doing calculus on space curves. In particular, we'll talk about differentiating space curves, which would be the first calculus, I think, that you've done this semester in Calc 3. Okay, space curves. So I think the easiest way to think of a space curve, at least to begin with, is I don't know, like maybe you're sitting out on the edge of town and there's a hawk sort of circling up above a wheat field looking for dinner. Imagine that hawk as a point in space, and imagine that you watch that hawk for, say, 10 minutes. At any moment in time, that hawk has a position in space relative to, say, you, where you're sitting in the wheat field or something. In fact, that position is described by 3 numbers, x, y, and z, right? Again, assume we picked a coordinate system and maybe we've rooted it at our location sitting on the wheat field. those positions, those coordinates, x, y, and z, are all changing with respect to time as the hawk circles the field. This is what we want to begin to understand. If you freeze a moment in time, if I pick a time, say 1 minute into my observation, I can plug it into these formulas and I can get out the exact position of this hawk. That's what we're trying to understand. Moving forward, what we want to do is, there are lots of things that we'd be interested in there. One, we would be interested in if the hawk sort of just flies around for a while and pretend that it left a little trail behind it, and you watched it for 10 minutes, that trail would actually make a shape in space. It would have, like a ball of yarn or something. It would just sort of be all twirled up there as the hawk sort of soars around looking down. We're going to be interested in two large aspects of this trajectory. One, we're going to be interested in the shape of the trajectory, just as a whole. Not just a particular point, but take all the locations together. They form a curve in space. We're going to be interested in the geometry of that curve. And then we're also going to be interested in how the curve is traversed. Like, let's pretend that the hawk does a spiral, right? Well, did the hawk start down here and spiral up, or did the hawk start up here and spiral down? We're going to care about direction that we travel along. And did the hawk go along the spiral up, say, at a constant speed? Certainly didn't go at a constant velocity, right? Because if it was a constant velocity, then the thing would fly in a straight line. Okay, that's basic physics. But did it fly at a constant speed up the spiral or down the spiral? Or did it speed up really quick when it got excited and thought it saw a mouse? Or did it slow down when it got bored? Or did it rise really quickly when a thermal hit it? That kind of thing. Okay? Go ahead, Nick.
So it's sort of like a curved vector?
Let's say no. Let's say it's a collection of points, not a vector, but in fact a collection of points. But your intuition isn't far off, because one of the things we're going to use to analyze the speed and the velocity of this hawk as it goes along its curve is we're going to use vectors. In fact, we're going to use tangent vectors. Because imagine, for example, the hawk starts here and goes like this. At any particular point, there's a vector that's tangent to that trajectory. That vector is going to be really important to us. So we'll be talking about that as well. Okay, so without further ado, let me pull up a really useful application. It's out there on the web. Hopefully it will come up in finite time. Oh, that's right. This thing has issues when I move from one end of the building to the other. So let me hit the stop button, which I don't see at the moment. Thank you. Okay, turning off the networking, turning it on. Okay, that looks promising. Let's try this again. Okay, let's give Java a chance to start up. This is a Java applet, so you have to have Java installed on your computer in order to use it. And as you noticed, I got to this page following this link right here on the class syllabus. It's kind of weird. It launches this, it goes to this web page and launches Java, but then you have to kind of click again to get the application to actually start up. Okay, so here is a mathematical and visual description or demonstration of what the hawk might be doing as it's flying around in the sky. And I'm going to start off simple. So if you, I realize the font might be a little bit small here, but at the top I've got those three coordinates that I'm talking about, x of t, y of t, and z of t. And each of those three coordinates is going to depend on time, t. And what I want to start off with is a fairly straightforward curve, which you may begin to recognize as I type it in. let me change A to 0. Let me change B to, I don't know, 2 pi. 9. Okay. All right. I'm going to zoom out a little bit. Maybe one more. Let me change these guys. Okay. And let me slide this guy a little bit down. All right, so here's the hawk at time 0. And time is moving, and the hawk is flying. And it's just sort of in a holding pattern above the weave field. And notice when I go from 0 to 2 pi, I actually trace out this whole trajectory. Okay. Those of you that remember parametric equations perhaps remember that this 3 cosine t, 3 sine t is actually the parametric representation of what? It's a circle of radius, not 1, 3. Okay, whatever that coefficient out front is. Okay. Let's go do a little bit of review here and try to figure out why this is tracing out a circle of radius 3. Okay. So I have these 3 panels up above. I have the X panel, the Y panel, and the Z panel. And each panel is showing a graph of what that particular coordinate is doing at that particular time. And notice the time variable, the green dot, as I slide it back and forth, this guy is controlling all 3 coordinates at the same time. So as I slide this back and forth in the X panel, you can see it sliding back and forth in the Y panel and in the Z panel. So it's one parameter, t, controlling 3 variables, X, Y, and Z. One parameter controlling 3 variables. Okay, let's focus on the X coordinate and the circle. So let me draw out this whole thing here. Unfortunately, the person that wrote this lovely application did not put X and Y coordinates on his application. So we have to imagine them. But they're actually not too bad. This is the origin, and you can see the graph paper here. This is 1, 2, 3, 1, 2, 3. So each square in the graph paper is 1 unit. Okay, let's see if we can't better understand the relationship between these coordinates, x of t, y of t, and z of t, and what's being drawn on the screen. So let's start out at 0 here. What's the x coordinate when t is equal to 0? 3, right? And what's the y coordinate? 0. So yeah, the x coordinate is 3, the y coordinate is 0, and that's where we are. We're at 1, 2, 3, and 0. Now, what's going to happen as I slide this guy to the right? Oh, I've lost my green guy. Hold on for a second. What's going to happen as I slide this guy to the right? Well, the x-coordinate, which started out at 3, is going to drop down to, say, 0. And at the same time, the y-coordinate, which started out at 0, is going to go up to 3. And it does that in a smooth way. So the green dot, which is controlled by time here, the x-coordinate is going to go down to 0. The y-coordinate is going to go up to 3. And we're at the top of the circle, right? What are the coordinates there? 0, 3, right? 0x, 3y. Okay, I can keep going. Now, what happens to the x-coordinate as I go past this point? It becomes negative. So now I'm on the left-hand side of the y-axis. And the y-coordinate starts to drop towards 0. And when I get to pi, I'm halfway around the circle. And it just keeps going. It takes some work. It's going to take some work on your part to really understand the relationship between the coordinate functions, x, y, and z, and what's being traced out on the screen as a space curve. But it's worth it. All right, let me wrap this guy all the way out to the circle. let's talk a little bit about what's happening with Z. So this is a somewhat trivial space curve because it lives entirely in the XY plane. This application lets you grab the screen here and rotate it around and have a look at what's going on from different perspectives. And so what I'm doing is I'm flipping this thing around in 3 dimensions. And what I'm seeing is, in fact, yes, this is just a circle and it just lies in the XY plane and it's not terribly interesting. Okay. If I'm really careful, I can slide this thing up so that I'm looking at it right on edge. And then what I want to do is I want to change this to a 1. What's going to happen? It should jump up 1 unit, and it may be hard to see. So let's really, I'm going to hit the 1 and then see if we can see it. Okay. 2, 3, right? Not 23, but 3. Okay. So you can see what Z does in this very simple case. It takes the circle that was sitting in the XY plane, lifts it up a unit, lifts it up 2 units, can drop it down below the XY plane. I kept the Z pretty simple just to start out with, but what do you think will happen if I change this to, say, T? Yes. So let's do that. So we put T in there, and you look at this and you think, wow, nothing really happened. Nick?
It's because you can't see it top down.
Right. I'm staring at this thing top down, so when I'm looking down on this, what am I looking at? I'm looking at the XY plane. Now, by all rights, and there's a little detail here that I'll talk about in a minute, by all rights, putting T in there shouldn't have changed anything about this shape from the perspective that I'm looking at it right now. Right? Because I didn't change X and Y, and therefore it's what it looks like in the XY plane shouldn't change. You'd notice, though, that it did change a little bit. Watch really closely if I do 0, and then if I change this to T. It moved a little bit. I just want to give you a heads up here that the person that wrote this application had to make a decision. And the decision was as follows. Do I want sort of a mathematically precise representation of the projections, or do I want something that looks good in 3 dimensions? And this person decided, I'm going to choose to make this thing look good in 3 dimensions. And one of the things that programmers do, and you'll see this in your video games or what have you, they try to provide perspective in their 3D renderings. What does that mean in a context like this? What it means is stuff that's the same size, right? When you're rendering on a computer screen, if this guy is further away from your perspective than this guy, then you want to make this look bigger and this looks smaller. And that's what's going on here. I'll explain that a little bit more in a minute. So we changed this thing to T, and we see that, in fact, this is a spiral. Technically, we call this a helix. Okay, this is a helix. The helix, when you look down on it, looks a lot like the circle that it came from. The big difference is you change that Z coordinate, and now it's no longer just sitting in the Z axis as the angle increases, but in fact it's, no longer sitting in the XY plane as the angle increases. It's now rising out of the XY plane according to the angle. So let me slide that back a little bit and you can see. As I increase the angle, not only do I move in a circular fashion in the XY plane, but I rise up out of the XY plane. Okay, so here we have a spiral. We've gone around a few times, and you can really see it now, this effect that I was talking about. If this were a true representation of the projection into the XY plane, that would just be a circle, right? But what we see is this sort of spiraling effect that's not real. This is an artifact of the guy trying to show you close stuff big and far away stuff small. So the green guy is closer to us, right? The green dot. And so it appears, the circle that it's tracing out appears bigger than the blue dot way at the back. And that's what's going on there. So just be aware that that's an effect that's built into this application. You may be able to turn it off, but I'm not really sure how. So that's a helix. Let's play around with this a little bit. How about if I take this and change it to t over 2? What do you notice? It squished it together, right? The reason for that, qualitatively, can you tell me why that got squished together? Over the same t interval, z only went up half the rate. Okay, and so I can actually squish this down quite a lot if I want. And then I can keep winding it out if I want to. Okay. I could stretch it out. Right now it's really sort of stretching out into space. Okay. And I could bring my B back a little bit, maybe 8. Okay, and you can see how it stretches out. But if I look at it from the top, again, I have this perspective problem. From the top, that should just be a circle, right? But I've got this slight perspective issue. In fact, you can even see it. The green dot is much bigger than the blue dot because it's closer to us. All right. I like this other one better. And maybe we'll make this like 80. Is your car parked on the railroad tracks? What else could we do to this thing?
Make the z a function, or like a function that loops back on itself, like cosine or sine.
Sure, let's see what that does. So if we change z to something periodic, so now you see the z coordinate has got this this oscillation, and yeah, if you look down on the top, again we've got this perspective problem. But let me back off a little bit. Let's go 6.29, which is like 2 pi. Let me go to 0 here. You see that, roughly speaking, it looks like the circle that it is, the circle of radius 3 from above. But if you tilt it from the side, you start to see that the z-coordinate, what's the z-coordinate doing in this picture? It's oscillating, right? And as you go around the circle, right, so you're going around the circle, and now suddenly you oscillate, right? You get this figure. Okay, I could make these oscillations even more striking by just cranking up, you know, make this say 10 or something, and yeah, it's like a little crown or something. And then you can see as I move this guy around, right, it's going around the circle, and at the same time its z-coordinate is going up and down. And you can just keep going around and around and around and around and around. Okay. Yes. We could combine this with, come on. We could combine it with the helix. So we've got oscillation and we've got growth. And let's see here, we probably have to run this out a little bit. Let me back off on the oscillations a little bit here. Let's go down to 3, say, and then you begin to see, you know, so it's going up and down, and let me knock back the oscillations a little bit, or the amplitude a little bit. So let's maybe make this 10, and that's a little bit better.
How do you make the
Like the Pringle shape.
Yeah, the Pringle shape, huh? Okay, so the Pringle shape. You could do something like this. You could do something like this. This is not quite Pringle.
Oh yeah.
Close enough.
Because from the top, what's a Pringle look like?
Doesn't look like that.
Right. I know it well. Yeah, so can I make it from the top look like an ellipse?
Could you make the sine and cosine, the x and the y bigger?
Yeah, just change what?
So now I've changed one of these guys to a 2, and I'm not, yeah, I guess I'm kind of there, no?
You have to envision
Yeah, but still, it's still not quite right.
It needs to be less. The Z is too steep. It's really gently.
It's also the case that these peaks aren't really quite where they're supposed to be. Right? The side peaks are actually at the same position, and these side peaks are sort of offset a little bit. So you've got to work harder to get a Pringle. They are, yes.
It's a mathematical shape, though.
Oh, it is. It's a very interesting shape, which we'll talk about Pringles later in the semester. In fact, maybe we'll have actual props.
Exciting.
It would be exciting, wouldn't it? Okay. So, yes, possibly we could trace out a Pringle with this, which would be really useful and just such a great application. Okay. Anything else we could do with this thing? Here, I have an idea. Oh, wow, that was kind of cool. I was just in the middle of doing something there.
Give us a symmetrical name.
It's pretty.
Ends will probably be set.
Let's do t squared, and then let's go back to 0 here. And then let's let a be -2, and let's let b be 2. And then let's look down on it from above. What do we have? Parabola. Yeah, so our friendly functions like y equals x squared and y equals cosine x, all of those can be considered space curves as well. They live in the xy plane. Their z coordinates are always 0, but you can think of them as space curves. So here I just took the friendly parabola y equals x squared and I parameterized it, meaning I let x equal t, and then in the y slot I just plug that into y equals x squared, I get t squared. And then the z slot, I'm just keeping it in the xy plane, and here you have a parabola that's a space curve. And you can slide this green guy back and forth, and it's a trajectory. Okay? Okay. Any curve that you can think of in the xy plane can be parameterized like this. Let's do sine of, say, 5t. Okay, so there's a curve in the xy plane that just looks like the sine function, but living in full three-dimensional space, you can twist this thing around and have a look at it from a lot of different perspectives. In fact, it might be worth talking a little bit about that. From this perspective, I'm looking down on the xy plane, but I can, with the mouse, I can grab that y-axis and I can actually drag it so that it's pointing straight towards you. If I do that, what's this curve going to look like? Yeah, I'm going to lose all of that detail. Can't quite get it right on, but there, that's close enough. I'm going to lose all that oscillatory detail. So in this view of things, it doesn't look very interesting. And that's why you have to be able to manipulate these things to really get a full idea of what they look like. I can do the same thing in the other direction. So here I'm back looking in the xy plane. I could grab the x-axis and drag it out towards you. And it's the same thing. What I'll be looking at is a little line segment. Right? And if you look at it in this direction and you drag this green guy around, it just looks like a little oscillator, a simple little oscillator. You don't see that motion. It looks like maybe something that's bouncing on a string or what have you. Okay, so there are a lot of physics applications to this kind of stuff. All right, that's not what I want. I want this. Yeah. Okay, oh, one last comment here. Let's look at, I don't know, let's look at this guy, T and T and T squared. T and T squared. And let's stretch this out a little bit. Okay. I don't know. Let's look at it in the XY plane. In the XY plane, it looks like a line. Does that make sense? That's y equals x, exactly right. So one way to visualize what this thing would look like in the XY plane is to simply set z equal to 0. Yeah?
Are you real quickly jumping back and forth?
There's only one default perspective, and that's looking down on the XY plane, and it's Control R, and you can get it from reading the instructions on the web page. So yeah, when I hit Control R, it immediately jumps me to looking down on the XY plane. Okay. Now, from this perspective, there's stuff that's hidden from me, right? What I don't see is the fact that the z coordinate is actually dropping away from me, although I can see the dot getting smaller, near the bottom, and then the dot's going to start getting bigger as it comes back towards me. But I don't see that really from this perspective. Okay, what happens if I change this to say, so let's go back here. What happens if I change this to say 3 star T, 3 star T, and 9 star T? And let me zoom out a little bit. Okay, if I do that and I slide this thing, it looks basically the same, right? The curve that's being traced out is geometrically the same. Well, roughly speaking, it's geometrically the same. What's different is the speed at which I'm going along the curve. So this guy is moving 3 times faster along the curve than the other guy was.
So you think all the points are in the same position as the previous equation?
They're all in, all the points are still there. They're still traced out. But I visit them at different times.
Third of the time.
Okay? Yeah, 3 times faster. So how did I get from that one to this one? What substitution did I make?
For the function like x of t, y of t, and z of t, you put in 3t?
3t, exactly. And when it got to the last one there, I plugged in 3t for t. That turns into 9t squared, right? This is called, this is essentially a different parameterization of the same curve. And it has no geometric effect, right? It looks exactly the same as it did before. The same points are present. The difference is those points are traversed more quickly. They're traversed 3 times faster. So if I'm looking at the hawk and it traces out this trajectory in one parameterization, it would trace out this trajectory 3 times faster. So that's another issue that we're going to be getting into as we go through this chapter is not just what shape is traced out, but how quickly is it traced out. Any questions about that? All right. So now what I want to do really briefly is just show you a different application so that I can get the axes in there, because that guy didn't have axes on his application. So this is a piece of mathematics software that we have in the math department. Those of you that take Calc Lab, if and when you take Calc Lab, you'll learn how to use this. And let me go and open up. Oh, you know what? I think I have. Oh, there it is. And let me turn all that stuff off. That was me just playing this morning. Okay, good. So let me put together, say, our friendly helix. Cosine t, sine t, t. In fact, let me put the 3's in there as well. All right. Okay. And let me turn on the axes here. Let's go with these guys. All right, so here's the x, y, and z axes. If I look at it from the top, in fact, I can control that with this right here, 0 and 0. If I look at it from the top, again, it looks like a circle, but even Maple is trying to do that perspective thing with you. So just be aware of that. From the top, this should look like a circle of radius 3, but Maple is playing that perspective game with you as well. And to be honest, if you turn it off, you can actually turn it off in Maple, and I don't remember how to do it off the top of my head. If you turn it off, it doesn't look as good. So you do notice it. But it's hard to talk about things like projections, which is what I want to talk about right now. What does that look like? Yeah, it looks like a sine or a cosine. In fact, it's probably a sine, right? Because we start off at 0 here, and it goes up out to 3, and then down to 0, and then down to -3, and then to 0. So this is sine. What do you think we're looking at here? Which plane?
XC, because there's no wedge.
I think you can tell.
It's XZ because Y equals T.
Well, did we decide that this was sine or cosine? Sine. That's a hint. This is YZ. This is YZ. Okay, because in YZ, it just looks like the sine function. Okay, let's spin it around here, and let's see what it looks like in XZ. That's XZ. How can I see that? If I want, I can just set the y part to 0 and try to figure out what curve that is. Okay, so I can ignore the y coordinate and just try to figure out what curve is left. Let's do the last one, which we've already talked about a little bit. So there's the xy plane. That means I ignore t, and I've got a circle of radius 3. Okay, the book, there are some exercises in the book that ask you to go through exercises just, that ask you to go through thought processes just like this. You have to be able to recognize parametric curves, and that's where you might want to get back into section 10.4, because there are some common parametric curves that are discussed there, and that might help you identify some of the curves that you're asked to explore in these exercises. Okay, any questions about that? So that's the reason I flipped over to this, is so we could really see the axes, because we can't really see them in that other application. Another reason to flip over to this is those little black arrows. those are going to become really important to us very soon. These little black arrows are tangent vectors to the trajectory, to the curve. And we're going to start caring a lot about those. But before we do that, let's review a couple of some of the exercises at the end of this section. Just talk about them in broad strokes so that you'll be able to do your homework. And then I'm going to come back and talk about these little black arrows. All right. Let's go here and here. And I'm going to switch over to note-taking mode here. All right. And come on. So we've got these guys, and we're going to start talking about them in the notes here. All right. I didn't assign, I don't think I assigned anything from, maybe I did, let me check. Sorry, I did. Assigned 1 through 4. Let's talk a little bit about 1 through 4. They seem somewhat ambiguous at the start. Investigate the curve. R equals sine t, cosine 8t. All that word means is understand it. What shape does it trace out? Do you understand how the coordinate functions are related to the shape? You've seen this one, right? What is, describe 1 to me. It does depend on how you look at it. So let's work that out. How do you want to describe it to me so that I understand what it is?
You're looking at xy, it's a circle
Of radius
1,
centered at
the origin.
good.
If you're looking at xz, it's a ellipse with major axis.
It's harder in XZ. It's not an ellipse. Okay? But that's enough. Let's just stop with XY. So in XY, it's a circle of radius 1 centered at the origin. What's the Z coordinate doing? It's oscillating up and down, right? So this is one of those crown-like curves that we saw earlier. And it oscillates 8 times as you go around the circle. Okay, and that's enough. That's an investigation. Okay? Well, I'll leave the others to you. If you want, you can plug these guys into the applet that's online, and you can get a really good view of what these things look like. But don't just plug them in and walk away. Plug them in and think about why they look the way they do. That's what I mean by investigate. That's what the book means by investigate. All right. This figure 13.2 we just discussed a little bit. That's a projection. 3 and 4 is more investigations. I wanted to talk a little bit about 5. I can't remember if I signed 5 either. I did. That's the star problem. Good. So let's talk a little bit about 5. Find a vector function for the curve of intersection of x squared plus y squared equals 9 and y plus z equals 2. What is x squared plus y squared equals 9? What kind of object is it? It's a circle, true, or it's a cylinder, also true. How can they both be true?
Z is, or I guess it's depending on how you look at it.
Exactly. Okay. So whether this thing is a circle of radius 3 or a cylinder of radius 3 depends on your context. The context here is 3-dimensional space. How do I know that that's the context? The next curve has an explicit z in it. So now we know we're working in 3 dimensions. Okay, so when you're talking about a circle in the xy plane of radius 3, and then you are and you're calling that an equation, x squared plus y squared equals 9, and then you say, oh, that's in 3 dimensions, what can z be? Z can be anything. So now you've got this one, and this one, and this one, and this one, and this one, all the way up, and this one, and this one, and this one, all the way down. And that sweeps out a cylinder. So that's why that's a cylinder. Context. All right. Y plus z equals 2. What is that? What kind of surface is that? Well, again, we have kind of the same issue here. It's a line in what plane? In the YZ plane, it's a line. But in full-on 3 dimensions, what is it? It's a plane, right? What's the generic equation for a plane? AX plus BY plus CZ equals D. What are A, B, and C here? 1, 1. Okay. Let's go over and do a little bit of work on how to visualize this thing. So this is not 12 anymore. We're on to 13 now. Okay, so this guy is a plane. At least in 3 dimensions, it's a plane. Okay. We're all okay with that, right? What's n? 0, 1, 1. N being the normal vector to the plane. What's a point on the plane? There are lots.
0, 2.
0, 2, 0. Certainly, if x is 0, y is 2, and z is 0, that point will satisfy the equation, right? Okay, what's another one? What'd you say? 0, negative 1, and
5, 7, 5, 7. But negative 1 and 2.
okay, and there are others. Any with non-zero x's? I mean, take any one of those other ones and change the 0 to whatever you want. Right? Okay, so there are lots. All right. But I am interested in, let's see here, can I get at, no, yes, I want to draw some axes here. Okay. And I want to call this the, oh, come on, go away. There we go. I want to call this, not the XZ, God bless you. I'm going to call this the YZ plane. What does this thing look like in the YZ plane? I like the way you think, yes. So solve for z, right?
And y, or the intercept 2.
So if I solve for z, I get z equals negative y plus 2. Why is that useful? Go ahead, it's your idea.
You can graph it really easily.
Right, what's the slope?
Negative 1.
And the y-intercept, or the z-intercept in this case?
2.
2, okay, so it hits this point right here, and this point right here, and just kind of, okay. What is that curve? What does it represent in the big picture? It's where the plane hits the YZ plane. Okay, so this is where the full plane hits the YZ plane. And then how does it extend? How does it turn into a plane? It just comes out of the board towards you, into the board away from you, right, along the x-axis. So that's what this guy looks like. Okay. Good. How do we... Can you get the cylinder in there to help you kind of visualize what the intersection looks like? Can you get the cylinder into this picture, and how do you want to do it? Let me remind you what the cylinder was. The cylinder was x squared plus y squared equals 9.
There's two little lines of three up lines.
Yeah, I like that. That's not the whole cylinder, but it kind of indicates where it lives. Okay, so the intersection of the plane and the cylinder looks like what?
Depending on your perspective.
Yeah, kind of depending on your perspective, I suppose.
Down the y-axis.
But it's really just like this thing tilted, like a circle tilted in a sense.
If you're looking normal to that,
So if you're looking, but if you look down from the top, right, and I'm not even going to try to sketch that in here. Okay, so you get the idea though that there's this. So now does everybody see the intersection that's being discussed here? Okay, let's talk about how to parameterize this thing. Think about it. Looking down from above, what does this curve of intersection look like?
Looking down from above, like down.
A circle of radius 3. How do you parameterize that? 3 cosine t, 3 sine t. So you've done half of it already. Sorry, you've done 2/3 of it already. Now all you have to do is figure out what does the z-coordinate do as you go around the circle. Well, it bottoms out down here at what appears to be -1, and it tops out up here at what appears to be 1, 2, 3, 4, 5. Can you make up a z-coordinate that does the right thing? As you go around the circle in the xy plane, can you make up a z-coordinate that goes up and then back down? Starts at -1, goes up to 5, and back down to -1. This is not the only way to do this, but I think it's a constructive way to think about it. So you've got the x-coordinate, you've got the y-coordinate in your star problem. Can you find me a z-coordinate that does the right thing? I don't want an answer. Okay. Okay, I'm just sort of presenting a way for you to think about it. Okay? Okay. Moving along then. Any questions before I move along, other than what the answer is? The answer is in the back of the book, so. Yeah. But it's a homework problem. Okay. Okay, let's keep going here. Problem 7, what's the difference between the parametric curves f, g, and h? I'll give you a chance to stare at them for a minute. While you're staring at them, I want you to think about, how did the author get from f to g? How did the author get from f to h? Okay, so how did the author get from f to g? Replaced all the t's with t squareds, right? It's function composition.
Is the last one a t squared or t?
The last one is
No, for g. G is t squared. T
I'm sorry, it's t to the 4th, yeah. The last one's t to the 4th. In fact, I can probably blow that up a bit by wiping this out. Okay. Yeah, all right. So is anything lost by replacing t with t squared? Yeah, right. T runs over all real numbers. So for example, the point -1, -1, 1 is on the curve f, right? Is that on the curve g? No. So in fact, all of those negative values are lost. And really what G does is it mimics the positive part of F, and by positive part, it mimics the part of F that corresponds to positive T. And then it actually does it, it does it again. It's sort of two copies of the positive T part of F. All right, let's talk about, so what's lost is all of the stuff that you would have gotten out of this if you were using negative T's. That's the geometry. What about the physics, the motion? What's different about the motion on G versus the motion on F? Kind of faster, although there are places where it's actually going slower. When T is between 0 and 1 on G, you're actually going slower, right? Because when you square something between 0 and 1, it actually gets smaller. But now when you get to 1 and beyond and you square it, it actually gets bigger. So this is a fairly complicated motion. It starts off slow, speeds up. When it gets to 1, for that instant in time, it's actually going the same speed as it would have on F. And then after that instant in time, it speeds up like T squared. Complicated motion. So not only do F and G have different geometry, right? The curves in space look different. They have different physics, different motions. All right, given that that perspective, let's think about how did the author get from F to H? Say it again. Sorry. Replace T with sine T. What have you lost geometrically doing that?
Everything that is in an output of that function.
Right, be more specific.
So for sine, it goes from -1 to 1.
Right.
So everything, any points beyond those two values.
Right, so any points that you would have gotten out of this from T's bigger than 1 or less than -1 are absent from this guy. Why? Because sine of T only produces outputs between -1 and 1. So for example, 2, 2, 4, which is on F, is not part of this curve because sine can never be 2. Okay, no matter how hard you try. And you have the same speed issues. The speeds here are different, and as T runs over all real numbers, this guy is going to trace out a curve and then sort of go back and forth, and it's just going to keep sweeping out the same little chunk of curve over and over and over again, right? Because sine is oscillatory. This guy, on the other hand, every point gets visited one time, only once, and it sweeps out a much larger curve as T goes from -infinity to infinity. So geometrically, what you're going to be looking at is a little piece. H is just a little piece of F. Just snip out a little piece, the piece of F that for T's from -1 to 1, and the motion is different. H is going to go back and forth across that piece over and over and over again, whereas F is only going to traverse that piece once. Geometry versus motion. Those are two different perspectives that are important here. We've got projections here. Let's finish with 9. Given 2 points in space, find the parametric equations for the line segment containing the points A and B. Be sure to give appropriate T values. Okay, on background, this is going to require you to use some skills that you picked up in Chapter 12. Where do you want to start with this? Just throw out some ideas.
Create a vector between A and B.
A and B, okay. With an eye towards what? What are you going to do with it?
I mean, you could subtract B from A, and then it would like be going towards B.
So I'll give you that. Either way is fine.
Yeah.
Now I've got this vector.
Well, in 1 unit of time, in T, 1 second, whatever, you've moved from
A to B, and so A1 has increased by the value of the vector between them and made it to B. So the slope of a function that's, or a line, if it's just A, going from the A value of A, the first one, to the X value, or yeah, of B, you increase by the little a value of the vector.
All right, so I've got this line segment, and what you're trying to describe to me is precisely what we did in section, I want to say 5. Does anybody remember what we did in 5 to describe this situation? The formula for a line. So let's go back to the formula for a line and see if that can help us parameterize this line segment. So do you remember how to do that? How to come up with the formula for a line?
So you don't find a parallel vector.
Yeah, we need a point on the line, and we need a direction for the line. We've got a direction. That's a vector, right? What's a point on the line? A or B, either one. And we'll vectorize it. Okay. And let me put that arrow in the right place now. Okay. So here's the vector that points to A. Here's a vector at some intermediate time, which we'll call L of t. And then there's the end of the vector, and this whole guy right here is just our n. So what happens as t increases? As t increases, this guy sweeps out the line. It goes in that direction, okay? All right, so that's the picture. Let's finish off the equation of the line here. A1, A2, A3 plus t times B1 minus A1, B2 minus A2, B3 minus A3. So there's a line that goes through the points A and B, but it does so much more, right? It goes off to infinity in both directions. And if you read this problem carefully, it says, give parametric equations for the line segment, even emphasized. Be sure to give appropriate t values. What are they talking about with appropriate t values?
If t was...
Nope, it's fine. Either one. Nick?
We need to just give like a range of values for t that's going to give you the finite segment, right?
Just the segment, right? Okay, can you figure out a range of t values that are going to start at A and end at B? If t is 0, where are you? A. And if t is 1, a convenient thing happens, right? All those minus a's cancel with the a's on the other side, and you're left with exactly B. Okay. The real reason I'm talking about this problem at all is give parametric equations. What does that mean? All right, give parametric equations. Whenever you're asked for parametric equations, what you're being asked for are the coordinate functions. All right. What is x of t for this for this line? Right. And repeat that down the list, and you've got the parametric equations for this line segment. And then how do you express the limit, the range of t's that you would like to restrict to? Mathematically, how do you write that down? Yep. And that would be a complete answer. The parametric equations for this line segment are x, y, z, 0 less than t less than 1, less than or equal to. Okay. Next time we'll talk about differentiating these space curves, and what you're going to find is a really beautiful geometric picture that shows that the derivative of a space curve is actually a vector, and that vector points tangent to the curve at the point. It's a generalization of what you learned in Calc 1. And until then, see ya. If you haven't turned in your homework yet, find the box and plug it in there. It's right there.
There we go.